Assalamu alaikum. Welcome, dear students, to our last part 6 in chapter 17 in Newton's laws. By the end of this video, you will be able to state and apply Newton's third law of motion, which is the principle of interaction on two interacting objects. Let's first start by reviewing together the main objectives of the previous videos. We've studied Newton's first law, which states that an object at rest remains at rest and an object in motion continues in a uniform rectilinear motion unless subjected to unbalanced forces. Also, we've studied Newton's second law, which states that the resultant of the external forces acting on an object is equal to the product of the mass of the object by its acceleration vector. Let's start now with our last objective in this chapter. Observe the following animation. Why do we move our hands in this way when swimming? Or in other words, do we always need to move the water backward to be able to swim forward? Let's have another question to think about. Why, as soon as the shell comes out of the cannon immediately moves backward? What is the reason behind this movement? I think everyone has an idea about the answers of these questions from the previous year, but follow with me to better understand some notes regarding our objective. In the previous videos, we have stated Newton's first and second laws. In our video today, we are interested in studying Newton's third law of motion, which is known as the principle of interaction, which you have already studied in grade 9. We will remember together this principle and focus on some important notes related to it. Let's start by observing the following example. When the boy jumps on the trampoline, he exerts a downward force on it, but at the same time, the trampoline exerts a force on the boy in the opposite direction, the force responsible for the upward movement of the boy. Then, there exists the force exerted by the boy on the trampoline and at the same time the force exerted by the trampoline on the boy. In fact, we cannot find a single force. That's because forces always exist in pairs. Then Newton's third law, or the principle of interaction, states that for every action, there is a simultaneous reaction equal in magnitude and opposite in direction. In other words, if a body A exerts a force on body B, Fa on B, then at the same time B exerts on A force Fb on A, such that Fa on B as a vector is equal to minus Fb on A as a vector. Let us take several examples. When pressing by your finger on a spring, two interacting forces exist simultaneously between the finger and the spring. The force exerted by the finger on the spring, which is the action force, and the force exerted by the spring on the finger, which is the reaction force, such that F spring on the finger is equal to minus F finger on the spring. Also, when you walk, you exert a force by your feet on the ground, which is the action force. In turn, the ground pushes forward on your feet with a reaction force which allows you to move forward, such that the force exerted by your foot on the ground is equal to minus the force exerted by the ground on the foot. Note that in the two examples, the two forces of interaction always act on two different objects and not on the same object. Now, to check that the magnitude of the couples of interaction are equal, we will have a very simple experiment using two dynamometers that can measure 10 Newton each. If we pull the first on one side, then the dynamometer indicates 2 Newton. But also the second dynamometer reads the same magnitude, which is also 2 Newton. Now, if we pull the second dynamometer with a greater force, this time the dynamometer indicates 5 Newton. But again, we find that the first indicates the same value, which is 5 Newton. This actually proves that the magnitude of the two forces of interaction are equal. Consider now a cart A which rests on a smooth table and a magnet is placed on its top. Another cart B carrying a magnet is placed beside cart A so that the two similar poles of the two magnets are facing each other. We notice that the two carts A and B move simultaneously in two opposite directions. Then, if body A exerts a force on body B, Fa on B, Then simultaneously B exerts a force on A, FB on A, such that FA on B and FB on A have same line of action, opposite directions, and equal magnitudes. But what if a block is placed on card B? The two cards are not identical anymore. Knowing that the two cards A and B are subjected to the couples of interaction forces which always have the same magnitude, you will notice in this case that card A of smaller mass moves with a greater acceleration than the heavier card B. Therefore, the two forces of interaction always have the same magnitude, but they do not always have the same effect. Now, before we move on to solving applications, it is important to mention this misconception between Newton's first law and Newton's third law. We must distinguish between balanced forces and the forces of interaction which are not the same. Balanced forces are forces which always act on the same object. Let's take this example. If we consider the person as a system, then there is two forces acting on this system. The chair pushes the person with an upward force which is the normal reaction force N, and the gravity pulled the person with a downward force which is the weight. Whereas if we move to the forces of interaction, these forces always act on two different objects. The person pushes the chair by the action force, Fp applied on the chair, and at the same time the chair pushes the person with the reaction force, the force exerted by the chair on the person. In the case of balanced forces, where the weight and the normal are both acting on the person, according to Newton's first law, the vector relation between these forces can be written as the vector sum of N and W is equal to 0. While in the second case, we have two interaction forces acting on two different systems, which are opposite in direction and equal in magnitude. Then, their vector relation is written in the form F chair on the person is equal to minus F person on the chair. And since generally we attempt to study the motion of a system, we therefore need to find the vector sum of the forces acting on this system. So, in this case, it is not useful to add forces acting on two different systems. Let's practice now by solving the following applications. Please pause the video and try to solve each application by yourself. In the first application, you are asked to explain, applying Newton's third law, each of the following situations. If we observe the situation, we will notice that the person exerts a forward force on the ball. So, according to Newton's third law, the ball simultaneously exerts a force on the person in the opposite direction, which explains the backward movement of the person, where the force exerted by the person on the ball as a vector is equal to minus the force exerted by the ball on the person as a vector. Now let's move to the second situation. In the second situation, we can note that the gases ejected backward from the rocket. The gases ejected backward exerts an upward force on the rocket, which makes the rocket takes off forward. Then the force exerted by the gases on the rocket as a vector is equal to minus the force exerted by the rocket on the gas as a vector. Now let's move to the second application. In the second application, we are asked to discuss the following statement. The force exerted by Earth on the apple is stronger than that exerted by the apple on Earth. Observe the figure carefully. This statement is actually not correct. It is in general a misconception. Since according to Newton's third law, the force exerted by the apple on Earth as a vector is equal to minus the force exerted by Earth on the apple as a vector, which means that these two forces have equal magnitudes. But the force exerted by Earth on the apple is enough to make it move toward the Earth, while that exerted by the apple on Earth has no noticeable effect on Earth. Now let's move to our last application, application 3. A book of mass m equal 1 kilogram is placed at rest on a table, given that g is equal to 10 meters per second square. In the first part, you are told that someone says Newton's third law is not applicable in this case because the two objects, the book and the table, are at rest, and we need to discuss this statement. Actually, I know that you know that this is not true because, as we have mentioned, the forces of interaction always exist between two objects, whether these objects are at rest or in motion. Now in the second part, we are asked to represent the forces of interaction between the book and the table. These forces are the force applied by the book on the table, which is represented vertically downward, and the force exerted by the table on the book, which has an opposite direction and equal magnitude, then it is applied vertically upward. This is the representation of these two forces. Now in the third part, our last part, we are asked to determine the magnitude of the force exerted by the table on the book. Then we need to deduce the magnitude of the force exerted by the book on the table. Actually, the force exerted by the table on the book is the normal reaction force N. Then let's consider the book as a system, and the book is at rest. Then, since it is at equilibrium, the vector sum of all the forces acting on it is equal to 0 vector. The forces acting on the book are the weight and the normal reaction force. Then W vector plus N vector is equal to 0 vector, which means that N vector is equal to minus W vector, and this indicates that the magnitude of N is equal to that of W, which is calculated as mass times gravity, which gives us 10 Newton. Then, returning back to the first objective in this question, the magnitude of the force exerted by the table on the book is equal to the magnitude of the normal force, which is equal to 10 Newton. Now, after we have calculated F table on book, applying Newton's third law or the principle of interaction, we know that the forces of interaction have equal magnitudes. Then the force exerted by the book on the table is equal to that exerted by the table on the book is equal to 10 Newton. Let's summarize the ideas of this video. We have studied that Newton's third law states that for every action, there is always a simultaneous reaction equal in magnitude and opposite in direction, such that Fa over B vector is equal to minus Fb over A vector as a vector relation. The couples of interaction always act on two different objects, so they have different effects if the two objects are not identical. Then, Newton's three laws of motion are Newton's first law of motion or the principle of inertia, where the vector sum of all external forces acting on an object is equal to 0 vector. Newton's second law or the fundamental principle of dynamics, where the net force is equal to the product of the mass of the object by its acceleration. And finally, Newton's third law or the principle of interaction, where the force exerted by A over B as a vector is equal to minus the force exerted by B over A as a vector. This is the end of part 6. Thanks for your attention.